Our lab for this week is a very beautiful chemical kinetics experiment that will allow us to learn and exercise the ability to interpret kinetic data, especially through kinetic models. The reaction in question is very nice for a bunch of reasons. It's simple. It only involves just mixing these two reactants. It produces a colored product, which is very brightly colored, in fact. And so that means we can follow the concentration changes in that product as a function of time by just following by just watching in a spectrometer, basically. Also, the reaction takes place over a relatively short period of time, and not too short, right? So some chemical reactions take place in milliseconds, some take place on a month time scale or something like that. Both of those are impractical for our purposes. This reaction takes place over the course of maybe about 15 or 20 minutes, reaches close to completion anyway in that time. And so that's a good time scale for us. It goes even a little bit faster when we raise the temperature, and that's also kind of nice, saves us some time. All right, so that's the chemical reaction. We have DNCB, has this labile chloride up at the top, or chlorine at the top, reacts with piperidine, forms this yellow-colored molecule, and a leftover protonated piperidine. I'm not so sure that the reaction itself is of great interest. What's of more interest is the ability to use this reaction to see how chemical kinetics experiments are done and how they're interpreted. All right, so yes, as I said before, it's just a matter of mixing the reactants together and following the concentration, the absorbance of one of the products as a function of time. It will start at near zero and rise up until reactants start to run out and the total amount of product starts to reach a steady value, a constant value. We'll use the fact that the absorbance is related by means of an extinction coefficient and a path length related to the concentration of the DNPP. That's the yellow product here. This is the DNPP. And so if we know the extinction coefficient, which we do, or we have a good estimate of it anyway, and we know the path length, which is 1 centimeter, then we can calculate what the concentration of the DNPP is at every point in time by just following the absorbance as a function of time. This is a standard sort of thing, and reactions like this that have a colored product are very popular for that reason. Oftentimes in kinetics experiments, the most difficult thing is finding a way to monitor the changes in the chemistry, in the chemical concentrations versus time. And a colored product or a colored reactant, either one, is probably the very best situation to do that. All right, I'm going to skip over much of this stuff because it has to do mostly with the details of interpreting the data, and I'll talk about that next Monday. This Monday I want to focus mostly on the minimum that we need to know in order to do the experiment. But let me just say that, okay, after talking about the nature of the chemical reactions that are taking place here, we can write down a 5-step mechanism, but one of those steps in the 5-step mechanism is a slow step. It's a rate-limiting step, or so we assume anyway, and the data are consistent with that, which means that all these later steps, these fast steps, don't affect the rate at which the products appear very much. This rate is a choke point. It's much slower than all the others. Once you've gotten past this step, all these others occur quickly. So they don't have much effect on the overall kinetics. This is often true in all kinetics experiments and something of a problem. I mean, it makes things simpler in our case, and that's nice, but if you want to know about these later steps, it means you've got to do something else because this slow step is sort of masking all the signatures and information in the kinetics that would be telling you otherwise about all these later steps. So if you want to learn about them, you got to change the experiment somehow. We won't do that. We're going to basically just focus on measuring this initial slow rate constant, which forms this intermediate and then goes on to form the product later, so DNPP here and here, once the intermediate is formed, once the slow intermediate is formed. All right. You can write down rate equations, a bunch of them. It's a good exercise. If you haven't done that in a while, it's a good exercise to take this 5-step mechanism and use those to write down these rate equations in general. In principle, it's possible to code these equations up on a computer and make predictions about the entire mechanism using those rate equations, basically by just integrating them in time numerically on a computer. And lots of people do that. There are standard software packages, in fact, that exist to do that. You can even write one of your own without too much difficulty. In fact, there are some trickinesses about that, but it can be done without too much difficulty, especially if you're aware of what the pitfalls might be before you start. But we won't do any of that, mostly because, yes, there's this rate limiting step, which means that we're really not going to get very much advantage by using this full mechanism. Then by making the approximations that will simplify the mechanism a great deal. The two approximations are the steady state approximation, and I'll talk more about that next week. But that simplifies these mechanisms a great deal, or all those equations in a great deal. And the second thing we're going to do is assume that this back reaction is very much slower than the forward reactions. And once you make both of those approximations in this mechanism, then this relationship, which comes from the steady state approximation, boils down to this quite simple relationship, and after that it's a matter of solving a differential equation. We will do that, and let me show you what the final answer is. Here's the sort of core expression. It gives the DNPP concentration, that's the colored stuff, as a function of time, and as a function of the initial concentrations of the piperidine and the DNCB. You can see those show up in several places in this expression. But those are known quantities. We know those ahead of time from the solutions we mixed. And so the only adjustable parameter in this expression is the rate constant, the slow rate limiting rate constant K1. So we're going to basically, what we're going to do is make measurements and then use this theoretical expression to fit the curves that we get from our measurements, and therefore extract values of this K1. For one set of cases, we'll do that as a function of temperature. So we'll have K1 at 3 different temperatures for the same reaction conditions, and that will allow us to get an estimate for the energy of activation for the reaction. Also a very useful thing to do. All right, so the 3 conditions we're going to consider, I need to say at least this much in order to say why we're doing what we're doing this week, is first of all a set of conditions where one of the reactants is at twice the concentration of the other one. DNCB is one of the 2 reactants that react to form the yellow stuff. Piperidine is the other one. When this condition is satisfied, that is when we have twice as much piperidine as we have DNCB, then everything is stoichiometric, and that simplifies the analysis a great deal. That's called stoichiometric initial conditions. That's one of the set of conditions that will set things up as. The second special case is what's called flooding. In that case, we'll put in a huge excess of piperidine, and over that, that is over the DNCB. So one of the 2 reactants is present in a huge excess. That means its concentration barely changes. When all the DNCB is already used up, the piperidine concentration has hardly changed. And that means that this second order expression up here, this one, this becomes essentially a constant, which means the whole thing behaves as if it were a first order expression. So that's another special case that we want to explore. And especially next week, we'll talk about what that means and how that's advantageous and so on. All right, so those are the two special cases. Then there's a general case where we don't have any special conditions, where we just mix a certain amount of both and let things run. And then that case, so these two special cases have special fitting functions. Here's one of them for the flooding case. And here's the other one. This is the fitting function for the stoichiometric case. And then there's the third case where nothing is special, in which case we use our general expression up here. The general expression will work even for the special cases. So in fact, what we're going to do is fit all of our data to this expression and then also see how good the fit is when we're using these less general expressions in the two special cases. We'll find out that the general expression works better even in the special cases, and that's basically because there are some errors that mean that we're not really truly in the special cases, and the general case works better in that case. But we will also see that these special cases come close in the special cases, that these special fitting functions come close in the special cases. So the analysis is generally correct. It's just better numerically to use the general case in all cases. All right, so here are the experiments then for this week. We will do 5 kinetic runs in this lab. We'll do the general case at 20 degrees, the stoichiometric case at 20 degrees, and the flooding case at 20 degrees. And what 20 degrees here means is this means lab room temperature, which we presume is close enough to 20 degrees. We'll write down what the actual temperature is so we know what it is. But it doesn't matter whether it's exactly 20 degrees or not. It's basically just room temperature, a known room temperature. And then we'll do 2 more, so that's 3 of the 5 runs. We'll do 2 more runs, one at 40 degrees and one at 60 degrees. We'll use the general case, not one of the 2 special cases, for both of those runs. That means that the general case will be done at 3 temperatures altogether, 20 degrees, 40 degrees, and 60 degrees. And that will give us enough data to get some information about the energy of activation using an Arrhenius plot. All right, here is the experiment. Let me switch to red again now. First of all, we're going to use the 2 spectrometers, one in room 280 and one in room B66 down in the basement. We'll use them both at the same time so we can not be wasting any time. Each group will use one of the 2 spectrometers. And in both cases, we'll set the spectrometer to read at a value of 472 nanometers. We're not actually taking a spectrum in this case. We're monitoring at one wavelength as a function of time. So we set the spectrometer to 472 nanometers. We could set it to some other value, but we know the epsilon, the extinction coefficient at that value. That's a known value. And that means that simplifies things for us quite a bit. So we use 472 because we know the extinction coefficient at that value. We could probably find it on the internet for other wavelengths, but, well, it's in the write-up for 472, so why not use it? Then what we're going to do is take a certain amount of DNCB stock solution, that's one of the reactants, and we're going to dilute it with a certain amount of ethanol, pure ethanol, right into the cuvette, no intermediate containers of any kind. We just take the cuvette, and there's a little table of how much to put in each case. You can see that in the write-ups. We put a certain amount of DNCB in, we put a certain amount of ethanol in, then we put that thing into the spectrometer and we zero it out so that when we know that there's no DNPP, none of the yellow stuff, none of the product present, we make sure that the spectrometer is reading 0 at that point. Otherwise, there would be little fake offsets. And so the first step is to zero out the spectrometer when only the reactant is present. And in fact, only just one of the reactants is present. Then we're going to spike that cuvette with a certain amount of the piperidine, and the reaction starts. The reaction goes pretty quick. So you have to do this mixing pretty fast, and there's several ways of doing it. I think the write-up says to put a cap on here and invert it, and that would work fine, but it sounds a little messy to me. An easier way is we're going to be using the pipetters, and so when you spike with the piperidine solution, just squeeze up and down a few times, suck up and down, and spit back out a few times, and that's good enough mixing as well. That takes a few seconds, and even in that few seconds, the reaction's beginning to happen. You'll see that when you put the cuvette back in the spectrometer, at least in some cases, it's already starting to turn yellow. And that means you're not starting from 0 time. That's something to be aware of when you're fitting your data, that you're going to have to get some kind of estimate of what that initial time actually was. It isn't quite 0. Your first few data points are also not reliable because things are still a little swirly in the cuvette. So the first point that you actually use in fitting your data won't be at time 0. It will be at some later time. Then we monitor the absorption at 472 for a specified time, and the times are down here. We'll talk about that in a second. Then save your data right away. I think one group 2 weeks ago or so had 3 weeks ago, had the unfortunate experience that once you have a spectrum, if you record another spectrum after that, the software doesn't save it, and so you lose it. So record it right away onto a thumb drive or whatever, and then rinse the cuvette and start over. Do the next thing. Now, one complication, and that is that only one of the 2 spectrometers has a temperature control. That means all the temperature-controlled runs have to be done on that spectrometer. So I have a little schedule here that allows both groups to basically be working full-time using both spectrometers. And the way that works is that one group is running on the temperature-controlled spectrometer, doing all 3 temperature runs. And the reason why we do all 3 at once is because the times for the higher temperature runs get quite short, and so all 3 runs take about the same amount of time as 2 runs at the lower temperature. At the same time, so this is the spectrometer in room 280. The spectrometer in room B66 will also be in use at the same time from the other group, whatever that happens to be. And that'll be at room temperature, and those are 30-minute runs for those 2 cases. Then the 2 groups switch. Group B comes up to 280, Group A goes down to room B66, and we just repeat everything with the spectrometers switched. Let's see. Amy and I will be there to make sure everything is going okay, but I think the actual experiments are pretty quick and pretty straightforward. It amounts to running the spectrometer, mixing some solutions. The stock solutions will already be prepared when you get there, so you don't even have to do that. You can see it takes about 2 hours out of the 3, and so we've got a little bit of spare time. That's always a good thing because things can go wrong. And then you're going to do some data analysis. I'll talk much more in detail about this next week, but here's a little overview of it. You're going to get a bunch of curves. Basically, it's going to be absorption versus time curves, 5 of them. And the first thing you have to do is convert the absorbance into concentration, right? It's DNPP concentration that we're actually going to be fitting. Use an extinction coefficient of 360 molars to the -1 centimeters to the -1 in order to do that. So you'll have a column of numbers in your Excel spreadsheet, and you'll use a formula to convert that column into a column of concentrations right next door probably. You'll need the initial values for the DNCB and piperidine concentrations. Those vary from experiment to experiment, but since you know the dilution factors and also know the initial concentrations from the stock solutions, that's easy to do. Then you're going to use solver, or whatever other method you choose to use, to fit the curves that you have. So fit the DNPP versus time curves using the appropriate expressions. Always use the general case. That should always work. And then use the special cases as well when those are appropriate, for the cases where those are appropriate. You're going to get a K1 value from both cases, that means, for the two special cases, and sorry, K1. And you should compare those two. They won't be exactly the same, right, because you're not using exactly the same fitting function. And you should see how close they are. Probably the one for the general that used the general case as the fitting function will be the more reliable one. Let's see, yes, here's what I said already, that you have to estimate the true time at which, well, the true time at which you first start fitting the data. The first few data points are probably not reliable. They're oftentimes outliers. Don't try to fit those. You'll get bad fits everywhere else from trying to get those first few points that are probably in error anyway. And then, once you've got K1 values for everything, you'll have 5 K1 values. 3 of those will be at different temperatures for the general case. And you can make an Arrhenius plot, which is a plot of the logarithm of the rate constant as a function of 1 over temperature. If you look at the Arrhenius expression here, that should give you a straight line. The slope of that straight line should be minus the energy of activation divided by the gas constant R. And it's that energy of activation that we're most interested in. Again, we'll talk about that more next week. So I think that's enough for going on for this week. I'll talk more about this tomorrow at the Zoom meeting. And good luck, everyone.